La la la. Okay, we're back. So now I put all of today's lecture slides on the website if you want to play with them. Alright, let me see, where are we up to? Oh yeah, which bar is the most popular? Which bar is the most expensive? Hopefully you might be able to see a way to do that pretty quick. Same kind of strategy, and maximum average price was what it's talking about. So we could write a view that said what's the average price of beers at a particular bar. Hopefully that's pretty straightforward to do, group by bar, using the cells relationship because that's where the price lives, and then select the average from that. And then once we've got that table, then we got the same kind of structure, which is the most expensive. So select bar from cells where select bar from the average price view where the price at that bar is equal to the select maximum price from average price. So that should be in here, which is the most Alright, so from the average price using the AVG, which is a built-in Postgres aggregate to compute averages. I think we've been using, so there's a few useful aggregates. Min, max, count and average are probably the most commonly used ones. So this will give us the average price for a particular bar because we're grouping by bar, and then we can use that to pull out the bar whose average price is equal to the maximum average price. It doesn't matter. Oh yeah, alright. And this is turned into that by virtue of the way that I define the view. If I hadn't put this, then the attributes of average price would be bar and AVG. So it would just use the name of the aggregate as the name of the attribute. Alright, so hopefully, that's really just a variation on the previous thing. So hopefully you're starting to see these patterns. Alright, which beers are sold at all bars? Now this introduces an interesting thing, the notion of all bars. And that might also appear in an information request as every bar. Okay? All bars, every bar. So we're interested in beers where they are sold in every bar. Now the way you solve this in SQL is a little bit obscure. What you have to do is you have to get a list or a set of all the bars, and then you need to get a set of bars where a particular beer is sold, and that'll give you two sets of bars, and if those two sets are equal, then the beer is sold at all bars. Okay? So how might we achieve that? Let's have a look. Which beers are sold at all bars? So that's basically the approach that I was just talking about. Get a set of bars where beer B is sold, get a set of all the bars. If those two sets are the same, then clearly that beer is sold at all the bars. Alright, so here we've got our correlated subquery. So we select from beers where there's some condition involving B. Now, what we've got here is an equality test on two sets. So set A is equal to set B, that's nice. Unfortunately, Postgres doesn't provide that set equality test, but what it does provide is set difference, and it provides effectively a test for whether a set is empty. Okay? So if we take the difference between the two sets and check whether it's empty, then that's we're achieving the same result as that. Okay? Set of all bars, subtract the set of bars where beer B is sold, and if the result is empty, then that beer must be sold at all bars. If it's not sold at all bars, then the result of that set difference, there'll still be some bars left from the all bars set. Alright, so the solution, and the way we check for a set being empty is we check that there are no elements in the set. So no elements exist in the set that we get by taking all bars and the set of bars that sell a particular beer. So here you can see we've got the correlated subquery coming from that. So this is going to give us set of all bars selling this particular beer, and take a set difference, and the syntax for that is except. Hopefully I talked about that. So you've got union, intersect and except. They're the three set operations that Postgres provides. And as the comment there says, that set difference. And effectively that test there is saying, is the result of this set difference empty? And if it is, means that particular beer was sold at all bars, which is what the question was asking. So that's a little bit of a stretch from what you have seen before, but that strategy works pretty much everywhere where the information request says all bar or all x's or every x. Okay, so you can get a set of x's, you can get a set of all x's, you can get a set of x's that satisfy a certain property, and check whether those two things are the same by doing that set difference. Now there is another way you could approach this, which doesn't necessarily work every time. Rather than getting sets, you get just counts. So you count the number of bars, the total number of bars, you count the number of bars where a particular beer is sold, and then check whether those two numbers are equal. So that would also solve the problem to some extent. Why are we counting? Alright, so this is introducing extra stuff. So we're using the cells relation to get, and grouping by the beer to get, for a particular beer, all the bars that it's sold in. And then we're checking using the having clause, which remember is effectively a where clause but working on an entire group coming out of a group by. So you're checking a condition on the entire group. So the condition is that we're counting the number of bars in the group, and effectively that's counting might have even got it wrong. We want to count the number of, oh no, that's alright, you shouldn't be selling a particular beer multiple times for different prices at the same bar. So so I think if you were worried about that, you could always add the word distinct, just to make sure that the number of different bars that sell the beer count distinct bar. But anyway, we're counting the number of bars that sell this particular beer, in other words the size of that group, and then we're checking whether that's equal to the total number of bars. So select count star from bars. This I think works in this case, but I'm not sure that it works, that it always works. So actually we haven't run this, have we? Just to prove that it actually works. And it's possible, and I think it might be true, that the result is empty. There is no beer that's sold at all bars. Let's if there's one that comes close with I can't remember the total. No, we'd have to do some hard work to make everything sold. We'd have to add a few tuples. Oh, we could try it. Let's. It seems to sell the most distinct beers, so maybe we can get there without too much effort. And let's say Kujibay Hotel is price gouging and it charges $20 for a Synchronous mark. What else? 3 sheets. There's another one that we need to add. That's only $10. Right, let's try that query again. Let's see. No, still haven't got it. Let's have a look at this. What other beer? Oh, Burgering Bock. That's the other one I need. Do we sell Kujibay? New, old, Victoria Bitter? Oh, that's. Are there any other beers? Not. Type. Get it cheap. Right, let's say that's $10 and let's try one more time. If that doesn't work, I'm going to give up. I'm going to give up. But we could sit there and we could, oh yeah.
Is it because you're adding beers when you should be adding places? Because you're trying to find beers sold at all bars.
Oh, I'm doing the wrong way. Oh yeah, duh. Good point. Thank you. Yes, I was trying to set it up to answer the query. Find a bar that sells all beers. Ah, all right, that changes things. Let's. Alright, what's looking plausible? That's sold, new is sold at a lot of places. What are we missing? No. Needs, no. It's too much work. Make an exercise for you. Try adding beers to this database until that query actually gives you a result. Yeah, I had a database where there was a result, but it's going to take too much effort. Alright, let's see. Which beers are sold at all bars? Price of the cheapest beer at each bar. That sounds kind of familiar. Each bar sounds like we're talking about correlated sub-query. Cheapest beer sounds like we're searching for a minimum. So let's take a look. Price of cheapest beer at each bar. Pretty straightforward, just group by the bar. Using the sales table, that gives you all the beers sold at a bar, and then just find the minimum price. So that'll give you the bar and the minimum price. Price of cheapest beer at each bar. I haven't got the solution here, but it's pretty easy. Select. Minimum price of cheapest beer at each bar. Okay. That's not going to give me quite the right result. Oh no, that's already solved the problem. No wonder I was tending towards that as my solution, because that is the solution. Oops. So that's the price of the cheapest beer at each bar. That's easy to get. If we want to find out what beer that is at each bar, or rather what beers that is at each bar, then we have to have a correlated subquery. Ooh. Alright, that was pretty exciting. Name of cheapest beer at each bar. So one thing we can't do is simply chuck in the name of the beer and try and do something like this, and that would not work anyway. But do something like that, because that's going to tell us, it's basically going to group by beer and bar. So we're going to, every beer sold at every bar is going to have a single price, and that's going to be the minimum price for that beer sold at that bar. So that's not at all interesting. That's going to give us a result for every beer sold at every bar. So we've got the cheapest view up here. Right, so cheapest, I might just copy this down. So the only way we're going to get this type of stuff is from the cells table, where the price of this beer at this bar happens to be the minimum price what did I call it? I call it price, okay. Hopefully that's correct. Where the price is the cheapest at that bar. And I might actually, so we can cross check, I'll just print everything. So beer, bar and the price. Notice that you can qualify star as well. Normally I wouldn't need to bother with, I might need to actually give an alias for the cells table. Normally you wouldn't need to bother with that, but we need to have a name so that we can reference down in here. Wow. Yeah, because I didn't add it. Right, good, see? Learn to read the error messages. Cheapest does not exist. And it thinks cheapest is a relation because I said from cheapest. It's actually a view, but it's perfectly happy to select stuff from a view. Where are we? Now, hopefully, if we have more than one beer at a bar, both beers are going to be the same price. And if you wanted to go and check, just get the minimum price for each bar, you could run the cheapest query and then cross-check to make sure that it had fetched the right stuff. So the Lord Nelson, the cheapest beer is new. So we could quickly check that one. Stuff from cells. Right, so there's 3 beers sold there. The one new is sold for $3. That's the cheapest price at that bar. And you could go through and check all the others just to make sure that thing was working properly. So it's possible that you can get more than one beer at the same low price at a particular bar. Okay. So once again, you know, we're using these patterns over and over. Right, how many drinkers are there in each suburb? That's reasonably straightforward. I don't think I need to spend much time on that. So we just group by the address. So in this database, the address is just a suburb name. So select from the drinkers, group by the address. It'll put all the drinkers who live in a particular suburb together, and then we just count how many there are in each group. And that'll give us the name of the suburb and the number of drinkers. How many bars are in suburbs where drinkers live? Alright, so this introduces a new idea. Often we need to get a list of results from a join, even if some tuples don't have an entry in the join. Classic example would be, I want to get a list of marks. That's not a classic example. What is a good example? I don't know, maybe this one. Yeah. In any case, a straight join isn't going to work. If I join drinkers and bars, to get the suburbs where drinkers live, I'm only going to get the bars that happen to also be in the suburb where drinkers live. Now that wasn't what the question asked for, or yes it was. I'm going to miss suburbs that have no bars. So the suburbs where drinkers live, there's a whole bunch of suburbs. I want every one of those suburbs to appear in the final result. If there are no bars in that suburb, then I want to get a value of 0. Okay, so to do that, we need to use a new construct called an outer join, and in this case it's a left outer join because the left-hand side of the join, we're going to get a result for every one of the tuples there. The right-hand side of the join. If there's nothing on the right-hand side of the join that actually matches the suburb for drinkers, then we're going to still, the drinker suburb is going to appear, but there'll be a null. There'll be a single entry that has suburb for this drinker and null because there are no bars in that suburb. Alright, so let's have a look at the result we get from this. Alright, so we can see here's a person who lives in a suburb and there's also a bar in that suburb. This result's a little bit wacky because Gernot lives in Newtown. There are apparently no bars in Newtown. Patently untrue in real life, but right, that's what the database says. John lives in Clovelly. Apparently there are no bars in Clovelly, and just lives in Mossman where there are also no bars. Now I think what I might do is find a simpler database so that I can show the effect or the difference between join and outer join. So what's in our ADC here? Hack together an example on the fly. let's hope it works. Insert into. Now the S table looks like that. Right, so if I want to do a join on these two tables, typically, I mean, the join attribute doesn't have to have the same name in both tables, but if I wanted to, I could do a join from join S on R.A, so S.A. So I'm looking for attributes in the two tables that have common values for the A attribute in each table. So we can see that, oh actually I should have added another one, doesn't matter. That'll do. Okay, so in fact I will add another one, just insert into S. And let's run that again. Okay, so every time there's a tuple in S that has the same A value as a tuple in R, we form, if you like, a concatenated tuple that has the values from one tuple in S and the values of attributes for one tuple in R. So in S, let's see what it looks like. So we've got two tuples that have an A value of 1, one tuple that has an A value of 2. So you can see that we're getting that result there. And in the R table, we've got one tuple that has an A value of 1, one tuple that has an A value of 2, one tuple that has an A value of 3. Alright, so that's what we get for a join. You can see that there's no tuple that contains 3 because there's no matching tuple in S that has an A value of 3. What an outer join is going to do, and I have a bad feeling that I got the syntax wrong, but we'll see. No, I haven't. Alright. So now we've got 4 rows. Here we had 3 rows, now we've got 4. So we've got exactly the same results as we get for the regular join, but if there are other tuples in R that don't have a matching tuple in S, they still appear, but since there's nothing to match them with, then we just put nulls in the AX field that would have normally held values from an S tuple. Okay. Just to see the difference again. So always with the join, we only pick tuples where there's a match in the join attributes. In the case of an outer join, we'll pick all of the tuples from R. All of those tuples will appear at least once. They may appear multiple times if they match with multiple tuples in the S table, but even if they match with no tuples in the S table, they still appear but with nulls in the places where the S attributes would normally appear. Alright, how does that relate to our beer database? And how does it solve the problem? Alright, we required that all suburbs appeared, all suburbs where drinkers drink, where drinkers live. So this, and we saw the result of that. And if I take away the outer join and just do a straight join, then I should get how many tuples? Only one, because there's only one suburb that has a drinker and a bar, and that's Randwick, so that one. see Randwick and Randwick. And here there's no bars, as I said, in Newtown. Surprising, no bars in Clovelly, no bars in Mossman. If there were, we'd get entries for them. And if there were multiple bars in Newtown, which is patently true, then we'd get multiple entries for Gurnot associated with each of those bars. Alright, so what have we got? So we've produced this. This is an intermediate way to our result. Remember the question was, how many bars are there in the suburbs where drinkers live? So these are the suburbs where drinkers live. These are the bars occurring in those suburbs. And what we're interested in doing, actually I might have, let's insert a few more. Insert into bars. Let's put some bars in Newtown. What's the name of the bar in Newtown? Who knows? No one. Alright. I think the Union Hotel might be one. And I can just make up the license number. And I have no idea.
Hive bar.
Hyde.
Hive.
Hyde. Really? In theory, these license numbers ought to be distinct, but I think the database hasn't actually specified that, so we're going to end up having two bars with the same license number because the schema didn't mention that they had to be distinct. Alright, so if we go back here now, we get the 2 Newtown bars because we've got a drinker that lives in Newtown. And if we go for the left outer join, where are we? Ooh, there we go. That's what we get. Alright, so now what we're interested in doing to answer the question is count how many bars there are in particular suburbs where drinkers live. Right, so clearly what we want to do, we want to form groups of suburbs, Newtown. If there were other drinkers who lived in Newtown, they'd be included as well. And then we want to count how many tuples there are in each of those suburbs. Alright, so there's one tuple related to Randwick, there are 2 tuples related to Newtown, and there are there's one tuple related to Clovelly and one tuple related to Mossman, but neither of those groups have any bars associated with them. So let me see. Give it a short name. DB has good. All right, nice to have an error. So we've got name here, address here, address here. Now we can get around that. Well, we could have got around it by not doing select star. That would have helped. But let's do quick and dirty fix. Phone, that's right. Right, so part of the problem was that we had 2 attributes called address. So if I rename one of them as suburb and rename the other one as address, then that ought to fix things. What? Oh. because of, yeah, alright, let's fix that. So in order to fix this, I need to qualify the so I need to say d.name drinker address, drinker phone, bar dot name, bar dot address. So it's not going to get confused now between those two name attributes. One of them's called d.name, the other one's called b.name. Hopefully that will solve the problem. Right, let's see what happens there. What? Really? Did it actually? Oh, it created it anyway. Oh. Alright, so now I can chuck in, create or replace. Now created it with that ambiguity. Alright, so now it's overwritten. Okay, the view had the same external structure as before, so I was happy with that. Alright. So now what we want to do, we want to group by the suburb and we want to count the number of bars in that suburb. So select suburb. Let's try that. Count the number of bars from DB. Group by suburb. And we get that. So, interestingly, and unlike a lot of the time when null crops up in SQL, generally where null appears, you're going to get a result which is null. In this case, the count aggregate sees null and counts it as 0. Okay. So, Newtown has 2 bars, Core Valley has 0, Randwick has 1, and Mossman has 0. So, couple of critical things there. The outer join to make sure that every suburb is included, and the fact that count understands how to deal with nulls. Questions? I can see people pointing at the screen. Got a question? No? Okay. Anyway, like I said, these are all in the solutions.sql, which is attached to, which will be attached to the website when I add the link. Have we finished? How many bars are we at? Alright, so we've done more. So a whole lot of interesting stuff cropped up there. The patterns for finding the name of the maximum thing, or simply finding the maximum thing. For every is handled by forming 2 sets and working out a set difference, which we have to express as not exists. An expression to give the set, then except, which is set difference, and then an expression to give another set, and checking whether the 2 sets are the same. Alright. So SQL, look, it's quite powerful. You can do a lot of things. You may have to express them in a slightly obscure way, but it's pretty good at extracting data from databases. However, that's not what you need in the real world. You need a way of interacting with the user, which SQL can't do except by running a select query from inside PSQL at the moment. That's all we can see. So those things are all there, but you can't write applications. So you need to have some way of including a little bit more programming notions into the system. So how might we extend SQL to make it better? One way is to add new data types. We've already seen that. We create domain, and there's some examples in the assignment. You can create enumerated types. We've seen that as well. You could add object orientation, which Postgres actually has. You can base the definition of one table on the definition of another table. So effectively you can subclass your tables. We can do a lot of interesting constraint checking with what we've seen so far, but there's some kind of constraint checking that we can't do, which I'll talk about later. Packaging up queries, okay, packaging them, here's a query, here's a name for it, that's fine. Parameterizing queries is something that we haven't looked at just yet. We want to be able to feed a value into a query from outside. Functions and aggregates, we've seen max, min, count, average. We might want to have other kinds of aggregates. And it's also useful, and this turns out to help solve this problem, but also to do other things. So for example, if you've got, in the bank example, you've got a whole bunch of accounts at a particular branch. Each account has a certain amount of money in. You also want to maintain the total amount of money held at that branch, and that's stored alongside each branch. The value that's stored there should be the sum of all the accounts stored at that branch. So, in Postgres and in most other DBMSs, you can set things up so that when you, for example, change the value change the amount of money stored in an account, what you're doing there is you're updating just the account tuple, but you can set it to trigger an update on the branch tuple to change the total amount of money stored at the branch to be consistent with the total amount that you've got in the accounts at that branch now. So triggers are important, as we'll see later on, and they're also useful for doing global type constraint checking. So SQL's nice. I think I've already said most of this. You can't even write factorial in SQL. Even factorial. Okay, you can. So, just to be annoying. Beauty. So you don't have to write factorial in SQL, it's already there, and it's there as an operator, looking like you'd expect. But you couldn't write your own factorial if you didn't like the one they provided. Actually, I haven't tried. Let's try and crank up. Cool, right? So you can probably, let's go further, see if I can break it. Beauty. Alright, so it'll just keep. So it's got arbitrary length integer values as well. Right, here's another example, and this is this bank account example. So we need to do a number of things here, and this will crop up again when we talk about transactions as well. First thing you want to do, you want to check whether the amount of money they're trying to withdraw is possible, because there's at least that much money in the account. So we can kind of get some part of the way. So notice you can have a constant as the result of a select statement. So what this select is doing, it's looking at the accounts table, it's looking at the particular account number that we're interested in, and you might say, how does that get there? You know, we'd have to type that in, and if the balance in that account is less than, once again, another piece of information that we want to feed in, if the balance is less than that, then the result is we produce this message. Ideally, this would be a test that had an if statement, and if it failed the test, we wouldn't do anything else. But SQL itself has no control structures, so regardless of the result of that, we'll keep going and we'll update the account, and then we'll print out the new balance. And those two things, okay, you want to do both of them, but you don't want to do them if there are insufficient funds in the account. So SQL doesn't cut it for that kind of thing, and that's even pretty simple. You know, if enough money in the account, then take it out. Am I transferring? No, I'm simply withdrawing, and then print the new balance. Otherwise, print an error message. SQL doesn't do that. So what we'd like is we'd like it to, if there were insufficient funds, we'd like it to just display and stop at that point. Otherwise, update's going to continue. So it doesn't allow parameterization, which is basically what I was talking about. Where do these come from? It's not like someone's going to sit there and type in the appropriate account number and the amount that wants to be withdrawn. We want to feed that in here somehow. It always does the update because we're not controlling the flow through the SQL statements based on the result of a previous SQL statement. I guess that's a minor thing, but we're evaluating, we're doing a database lookup twice when maybe we don't need to. And it always displays the balance even if we don't change it. So really it's not an adequate solution to that problem. So tomorrow we will look at an adequate solution to that problem using something built into the DBMS.